Alright everyone, today we're gonna do pressure 3.04 to 3.06. Let's go. Okay, 3.04, stretching and compressing. There are two types of materials. There might be more, they just haven't taught us yet. There's elastic and plastic. If you bend a ruler a bit, it springs back into its original shape. But when you bend it too much, it either breaks or becomes damaged and is deformed. This means that it is elastic. If you bend plasticine is Play-Doh by the way, it keeps its new shape. This means it's plastic. That's kind of weird, isn't it? Because you think, oh wow, ruler is made of plastic, but it's not plastic. It's elastic. That's like, whoa, right. Extension. When you hang a 1 Newton weight on a spring, the spring extends. We call the weight the load. Here's the weight, that little ball thing. That's the load. And the amount that it extends is the extension. Alright. Hooke's law. A material that obeys Hooke's law, if beneath the elastic limit, the extension is proportional to the load. Not all materials obey Hooke's law, only some. So as you can see, that's the extension, and that's the load right there, and it's proportional. You see, like you'll see. Okay, proportional extension. A spring will extend proportionally because it's elastic. For example, if there is 1 Newton weight, it will extend 10 cm, and when there is a 2 Newton weight, it will extend 20 cm. That's what it means by proportional. So if the weight is doubled, then the extension is also doubled, and if the weight is tripled, the extension also tripled. That's what it means. Alright, elastic point. With every material, there is an elastic point, where the object stretches too much and is deformed and cannot return to its original shape. So, on the y-axis is the force, and on the x-axis is the elongation, aka the extension. So right here is the elastic region. It's where whenever this much force you put on the spring, it will always return back. Right here, it's the, what is it called? Oh yeah, the limit of proportionality. This means, like, right here is, if it comes back here, if it goes up to here, it will always return to its original shape, and it will always extend proportionally. However, after that, it will not extend proportionally, and even after that, there is also the elastic limit, where it will be deformed and will no longer return to its original shape. After that, there is the plastic region. I think it's like, basically it turns from elastic into plastic, where it just changes forms now. And there's the breaking point over there, where it just completely breaks. Anyways, alright, spring constant. If we know the spring constant, we can predict how much a spring will extend. We can also predict how much the load weighs, and due to how much the spring extends. So yeah, here is the spring constant. The symbol is K. I don't know why. It's just, you just gotta say okay to that, you know what I'm saying? Okay, so like you see, it's F over X. X is the extension of the spring. So force over X is the spring constant. That's pretty easy. That's just force over extension. There you go. You can also rearrange it so you can get the extension. So force times the spring constant equals to the extension. And yeah, or you can do extension times the spring constant, so you can get the force. You can do many things with this formula. Compressing and bending. If an object is elastic, the object will return to its original shape, but if the force is too much, it will lose its shape. Alright, so just like, ignore these other things, but as you can see on B, there is compression, and D, there is bending. There's also, the tension, which is just stretching, and also there's shear, where you're like, kind of like pushing on both sides, but on the opposite ways. There's also E, which is torsion, which is just turning it. Yeah. That's basically it. Alright, 3.05, pressure. Pressure is a measurement of how much a force is there in a certain area. Pressure is measured in pascals. Okay, as you can see, there's this little cube thing pushing on this blue pad. We're trying to calculate the pressure of this thing, cube on this blue pad. The pressure is equals to force over area. Force over area. So the force, for example, actually not example, right? This is just a hypothetical. So the force over area, then you get a Pascal, which is also can be represented as newtons, newtons over meter squared. Pascals, sometimes pascals are too much, so they use kilopascals. Kilopascals are 1 kilopascal is 1,000 pascals. That's, yeah. Alright, so here's an example. As you can see, there are weights, there's the low pressure side, and there's a high pressure side. And there's an elephant there. I don't know. I was just too lazy to crop him out, so he's just there. Okay, so say the weights are both 100 newtons. Okay, that weight and that weight are both 100 newtons. The area of the low pressure side is 10 meters squared. So like you see that big block of wood over there? Yeah, the area is 10 meters squared. This means that the pressure is 100 divided by 10 because force over area, the force is 100 and the area is 10. Keep in mind that the area always has to be in meters squared. So if it's in cm squared, just convert it over to meters squared, or else you won't get an actual Pascal. Alright, so the Pascal is 10 pascals, 10 newtons per meter squared. That's the pressure on the low pressure side, and the high pressure side is, the area of the high pressure side is 5 meters squared. You see that small block of wood? That's 5 meters squared. I know it doesn't look like half of it, it looks more like a quarter, but just trust me, it is half of it. Alright. This means that the pressure is 100 divided by 5, and that becomes 20 newtons per meter squared. So yeah, 20 pascals. That's the pressure. The pressure is doubled because the area is smaller. That's, yeah. Okay, let's go next to pressure in liquids. Let's reverse a bit so you guys can get a head start. Here's the things you need. Here's density. You might have probably forgotten about it. This symbol is called rho. It looks like a P, but it's rho. Okay? And it's mass over volume. That's basically what rho is. And here is volume. You should know this already. If you don't, then what are you doing here? Alright, pressure. We just learned this like literally a slide ago. Here's gravity. Gravity is 9.807 newtons. And you know what? Just go on. Okay. How do you actually find liquid pressure? So the liquid pressure formula is rho gravity height. Rho times gravity times height. Rho is mass over volume, and gravity is gravity. H is height. So height, that's the fluid, and that's the object. So we're trying to find the pressure down here on the object. Why the formula is like that is here. So first, we need to calculate the volume. So base times height. So base, the area of the base is A, and the height is H. So and then the mass is so then we calculate the mass. So density times volume. So rho is density times so it becomes kind of. And then we get the weight, which is mass times the gravity. So gravity times rho times A times H. So it could and then the force on the base, and then we calculate the force on the base. So it's PG and the force is A, so the pressure equals to force over area. This is the force, and the area is A, so you cross out the A and it just becomes PGH. Yeah, it's just like algebra. Yeah, it's algebra. Here's some useful things to know about pressure. Pressure acts in all directions. The liquid pushes on every surface it touches. Pressure increases with depth. The deeper you go, the higher the pressure. Pressure depends on density. The denser the liquid, the higher the pressure. Pressure is not affected by the shape of the container no matter what. No matter the shape of the liquid, it will always have the same pressure at the same depth. So what the last point means is that as you can see on this here, the highest point, I guess you can say, is all the same pressure, and on the bottom is all the same pressure. Even right here at the bottom of A, where it looks like it should be more pressure, is actually all the same. Yeah, it doesn't matter. Here's an exercise. The density of water is 100 kg per meter cubed. What is the pressure at the bottom of the pool? What is the pressure halfway to the bottom of the pool? So the pool is 4 meters deep, is 2 meters wide, and it's 4 meters across. Okay, so let's move on. So the pressure is PGH. The density is 100 kilograms per meter cubed. The gravity is 10. Let's just use 10 because it's simpler. And the height is 4 meters. So the pressure at the bottom of the pool is 1000 times 10, the gravity, times 4, which is the height. So it becomes 40,000 pascals, aka 40 kilopascals. The pressure halfway, we already got the pressure at the bottom of the pool, so all we need to do is divide it by 2, because here, as you can see, 4, just change it to a 2, or we can take this and divide it into 2. I'll just choose this to divide by 2, so 40 kilopascals divided by 2, it becomes 20 kilopascals. Alright everyone, that's it. Thanks for watching.